I am Lito Michala. I am a lecturer at the University of Glasgow, and my talk today is entitled Tiny Data Collectors, Vastly Distributed Systems, and the Land of Tiny Challenges. Okay, I've made up some interesting titles, but hopefully they'll make sense as we go through. If anyone wants to know more about my research, that's my website there. And if there's anything you want to discuss as we go through the presentation, feel free to email me as well. So tiny data collectors, what do I mean? Obviously, I'm talking about the Internet of Things. And why do I call them tiny? Because they are usually embedded devices, though admittedly, some research talks about autonomous cars as also IoT, so they are not very tiny anymore. But I'll focus on smaller devices like your smartwatch or equivalent embedded type things that have sensors that collect some kind of information about either a specific application or generally the environment. Now, overall, my research focuses on three aspects of IoT systems, whether or not they are accessible, and I'm arguing right now that they are not very accessible, whether or not they are reliable, and within reliability, I'm going to talk about three things really: fault tolerance, security, and privacy. Whether they are understandable, so when we get data from those systems, the data we collect, can we trust it? Is it correct? Can we do anything to improve that? Can we understand how decisions are made based on the data that were collected from individual devices? And finally, yes, IoT systems are distributed, but certainly they're not quite yet decentralized. So I think these three kind of pillars of my research make for interesting questions around how IoT systems should be in the future. And I'll come to where Elixir fits in, though kind of reliability probably gave it away. Oops. Okay. So talking a bit more about IoT devices, I think there's a trend to increase the capabilities of these devices, even the small embedded ones, by either having more powerful CPUs, improved memory capacity, or even we've seen accelerators like GPUs, FPGAs, or even custom accelerators being used on IoT devices. So you can think of things like your smart cameras or the camera on your iPhone maybe is closer, where you can have filters, you can have all sorts of item identification running on the image that's streamed from the actual camera quite efficiently, quite quickly. So there is this trend, and on the other hand, there is a strain on cloud. And I think we haven't quite seen that yet. Everybody seems to just push everything, their data and their applications to the cloud at the moment, hosting whatever web services they are selling on top of the data they're collecting. But if we're going to talk about trillion of IoT devices pretty soon, based to the previous graph that we saw, I argue that we'll have problems with demand, problems with accessibility. Probably latency will start becoming a bigger and bigger problem as more and more users and more devices connect to those services. And at the same time, we have this pulling force of privacy that we've seen very recently, with GDPR regulation, how we collect data, how we protect the data and the rights of the users to whom the data belong, and so on. And finally, one of the other challenges for the cloud is that when data arrives to central points like the cloud, and if we don't know if this data is dirty or faulty or have any sort of history based on which we don't want to take them into account when we're making any further decisions on them. Let's call this dirty data. It's very hard to differentiate that from legitimate data on the cloud side. It's much easier to do that on the sensor side, provided we know the situation of the device that collected the data. For all these reasons, a lot of people are very interested in moving machine learning towards the edge. So on the graph, you're seeing moving the machine learning from the pink cloud, kind of vertical, towards the green or blue side, as far down the stack as they can. But I think we don't quite yet have a clear idea of what the edge will end up looking like. And I'll explain what I mean. So in a few, this is just a few publications from our group here at Glasgow in the past couple of years. In the first publication, our edge is basically a desktop machine that talks to small robot cars. And this desktop machine obviously has quite the capacity to run a sophisticated scheduling algorithm. The difference in that paper was that the scheduling of tasks takes into account things like how much power is still available in the battery of its robot, what CPU capacity is the robot running on at the moment, and what RAM utilization, so how much RAM is still free. And it's able to automatically produce variants of the task. So imagine the case of a robot needing to do some image processing to identify obstacles in front of it. We could examine the full image at full detail to do this job. But if the robot doesn't have the computational capacity or the RAM even to hold all that detail, we could do rough pixels of blocks of the image to try and solve the same problem. So we sacrifice accuracy to fit into the requirements of the hardware. In the second case, our edge is very different. So in this case, we're talking about microclusters. And by microclusters, I mean a set of Raspberry Pis. So we've put a tower of Raspberry Pis together and used it as a server to execute typical jobs you might find on a phone user, for example. So image processing, sound processing, kind of standard workloads you would probably expect to send all the way up to the cloud. And we started looking at, is there a latency improvement? Is the same scheduling approaches applicable as in data centers to these kind of smaller edge clusters? And our argument here was that maybe you have such a small tower that's not very expensive to put together in, say, a campus or a big company's offices to serve workloads for maybe your employees or your students or whoever that want to explore the space around them, to find things to attend and then navigate to them. So tasks that you would typically do, through Google Maps or something similar, rather than wait for service to connect all the way to the cloud, you could just connect to your local network and get service from there. So that's a very different perspective of what the edge is. Another approach of what the edge could be is the third paper I'm showing on this slide, where we're looking at infrastructure around roads. So, for example, you can imagine your lamppost being constantly located at one place. It might have an in-advance knowledge of the situation on the road before a vehicle approaches. So think of a lamppost on a curve. If the lamppost can have a camera to look at the other side of the curve, or any side of the curve, it could talk to an approaching vehicle and say that, look, a pedestrian is crossing right after the top of the curve and you can't quite see them, but you should slow down. So this improves safety for autonomous vehicles, but at the same time, it uses the edge as quite a different thing. It's only a small processor, not larger than, actually it's smaller than a Raspberry Pi. It's closer to an Arduino type processor or system. It's doing very basic processing on an image feed. And we're calling it an edge instead of an IoT device because its job is to talk to other IoT devices and to coordinate what they should do. So the definition of what edge is, I think, is quite up in the air. And also, now that I'm on a research exchange on a group that does infrastructure research, and they have even more questions like, should an edge device talk to an edge cluster and that talk to an edge desktop and whatever else we might have, and how could we coordinate all of that? So imagine our use case being this vastly distributed system where you are selling the same IoT device as a company throughout the world. And a classic example of that is a smartwatch manufacturer, and I'll come to that in a minute. The same device can be anywhere geographically, and for some of its workloads, it might need to talk to roundabout edge nodes, other IoT nodes, and we could imagine of a situation where things are super connected and distributing information between them. So this is not what's happening at the moment, by the way. Most of the IoT that's commercially available is pretty much just upstreaming all its data to some cloud service for which you then pay to get access to your own data or to get some service over the data and so on. But I'm thinking that in the future, to alleviate the stress on the cloud, we'll start seeing more of these architectures. And it's not yet quite clear how these might all talk to each other, how web protocols should be used, what's reasonable and unreasonable communication to be shared between these devices, what's too expensive in terms of what they can physically do and so on. And I think this is a very interesting if you like, landscape for further research development, but also commercial opportunities where Elixir might find a natural fit, or Erlang in general. So let's bring that back to kind of what's happening right now in real world examples. And I talked already about smartwatches. This is just me walking about in a park, wearing a smartwatch that records lots of very private data, like my heart rate, like my actual location. This is doing the typical thing, collecting the data whenever it finds available network or whenever I physically connect my IoT device to my laptop, it pushes the data back to the cloud. A more extreme case would be this. This is actually happening in Singapore right now. They are integrating IoT devices and edge servers throughout a part of the city to create what they call autonomous transportation system. It's not just autonomous driving cars, it's autonomous road assisted infrastructure, road assistance infrastructure, it's autonomous buses, autonomous deliveries, whatever you can think of. They are actually, they have turned a piece of the city into a playground for this. And they have several cars, some designed to deliver goods, some designed to deliver people. They also have electric driven buses that drive autonomously around, which requires a lot of things to talk to each other and a lot of things to share information. At the same time, it requires a lot of variable workloads to run on whatever capacity is available, right? So maybe a vehicle has already made a decision about a certain piece of the road. I don't know, it's closed or it has an obstacle that's not moving for another few hours. It can just give the result of that computation out to other moving vehicles in the area, or it could store that intermediate result in an edge service on a lamppost or a traffic light or whatever is available near it, and so that the next passing vehicle gets that information. So we're talking about the scenario where we're no longer just distributed by the fact that people need to provide data to each other, but we might also be distributed in terms of people needing to move workloads between each other almost opportunistically to take advantage of other available capacities or processors nearby. So I've just made this problem quite complicated, and then I'm going to make it a bit more complicated. So we're talking about this very, very geolocationally and very geolocationally distributed systems and very interconnected systems that, you know, I can't tell you exactly how they work because all we've ever tested is this pipeline here, IoT, some edge node vertically going up to the cloud. But if that wasn't enough, people want to move, as I said, machine learning and AI further towards the IoT side. So that means we no longer even propagate any data at all. We do all our information extraction right at the edge if we can, and then propagate extracted information. So we propagate knowledge, not data. And at some point further up in the pipeline, we aggregate all that knowledge to generate some global model, some global knowledge collected information that can be used. And this is what we call federated learning. It requires a new architecture compared to what people have been investigating quite a lot in recent years, because it requires, as I said, to break that data propagation up the chain. It might require a different or a multi-layer edge architecture or an interconnected edge architecture or something else to support it. It's still not solving the problem of the distribution. We're still very distributed throughout the world. But we haven't quite yet found out where we should aggregate this knowledge. Where is most advantageous to aggregate knowledge if we have, as I said, different users in different parts of the globe? Does it make sense to have one global model for all of the Earth? Or do we need, I don't know, imagine of a case where we have patient data and we know we have different diseases or different models of diseases in different countries. For example, we know there is definitely more diabetes in India than other countries. We know there are differences between countries. So does it make sense to have one global model, or would it be better to have a country by country model taking into account these differences? So aggregating at a country level cloud, not at a global cloud, if that makes sense. Also, we haven't quite discussed yet, well, yes, we want to move machine learning further back to the edge, but is the edge capable of running accurate enough machine learning workloads? How much computational capacity do we need to hit that sweet spot of accuracy? Or can we sacrifice accuracy because we're winning in power consumption? You know, we haven't quite answered these questions. And then the closer we go to the edge, the smaller the world of the machine learning task becomes. So the less data is available to it. And anyone who's done anything in machine learning has at least once heard that we need a lot of data to make machine learning work. So the aggregation task kind of overcomes that problem eventually by aggregating from lots of little things. You eventually have lots of data, so your accuracy should improve. But it doesn't solve the startup problem. So how does that model start when it only has a few observations from a sensor for the past few hours? What happens then? So then we have decisions to make. Should we even deploy these models on the IoT devices? Should we be talking about deploying them on the edge near them? And how many layers up the edge architecture is a good point to aggregate these things? There's been a few federated learning frameworks that have come up in commercial use in very recent years. I've named 3 here, which I think are the 3 most well-known. And I'm sorry if I have missed someone. But basically, they kind of share a few things. They are all pretty much targeting Python use. And this is for good reason, because kind of everybody and their granny are writing machine learning code in Python, because there's so many libraries available. There's so much there's pretty much no machine learning or AI problem you want to solve that you can't quite quickly solve using the available libraries in Python. So, and then it's an easy language enough to learn. So even people from non-computing backgrounds have quite adapted to the use of things like Python notebooks and so on to crunch their data. They say they provide some near real-time decision on data. They say they also support some network monitoring and metrics, but it's not quite to the level of reliability that we would like to see things, according to my view. Also, when they start talking about using Kubernetes and Docker, just imagine trying to put a Docker container on an embedded processor, and I think that kind of stretches its capacity to the point it can't even run the jobs you want it to run. So they're not quite targeting the IoT devices themselves. They are able to run on edge, if we're talking, desktop machine, laptop machine as your edge, then they are able to run there. And their huge benefit is that the data never leaves the data owner's machine. So if you have a little device attached to you that monitors your insulin intake, the data never leaves the insulin pump. It stays right there. It's your data. You can only get it out if you take the SD card out and plug it into a machine. It never needs to go anywhere else. So it gives you reassurance that you keep your privacy while the company providing decision support for your insulin or automatically controlling your insulin intake can still make useful decisions. So my land of tiny challenges, I'm talking to them about, I'm talking about tiny, not in terms of how difficult they are to solve, but in that they are tiny in terms of availability of resources. So there's tiny power in IoT devices, most of them at least, and we want it to be tiny because we want batteries to last for donkey's years. There's probably limited CPU. I mean, I don't think you'll have a quad core on a usual embedded device. Even though RAM is improving, it's not, you can't quite do tensor math very easily in milliseconds on an embedded processor. Networking might be unavailable or unstable. So I'm sure people have tried using even their Wi-Fi in a house that has big stone walls, like an old house, and that's not even working from room to room. So imagine having devices that are mobile. They might be, as I said before, my smartwatch, I might be wearing it today in Greece and tomorrow in the UK, and it has zero awareness of its environment or its networking connectivity changing or anything like that. So it can't, and then the last thing is, yes, we want to do more with them, but we can't make them very expensive. I mean, it's bad enough that this crisis has made all the materials expensive. Let's not make the software too expensive too. So we want them to be at a cost where people can buy them in volume. So trying to solve these challenges, I've looked at, do we even need machine learning on the edge, or can we simply do statistical processing? So I was looking at data that was coming in from vibration, from rotating machinery, and I thought, well, some of this data is not useful to any decision. So why do we even keep it? Why do we need them? And why can't we just look at profiles of data and hold on to these significant little changes that might make the difference between predicting a failure and predicting a healthy operating machinery? And in fact, this paper here, published in TIoT, shows that, yeah, we don't need machine learning for absolutely everything, and we don't need to keep all the data for absolutely everything. We can do it in very cost-effective, small computing units. They were unfortunately programmed in C, and oh my God, I know, I debugged those. But could they be better? Maybe. Could they be easier maintained? Maybe. I'll get to that in a minute. But yes, we can, and we don't need to use machine learning right on the IoT device. We can do the prelude to machine learning. We can do the statistical processing, clean our data, do lots of it on the IoT device within its capacity. And then another approach we were looking at was, how can we integrate machine learning in differentiating data that add value to a machine learning algorithm that further up runs in the cloud, and only hold on to that data, only propagate that data up to the cloud. But does that solve all the challenges? Not quite yet. So it only focuses on my little IoT devices. There's lots that I don't look into. For example, in this paper, we tried to start looking at the infrastructure itself. We started using blockchain and other things that sound interesting, but they come with their own set of challenges, as in, how much can you truly save on a blockchain? It runs to limits quite quickly. And then we have another big can of worms, which is GDPR compliance. And do we even realize or know, as we make our systems more autonomous, do we even know if they are compliant, and how can we understand if they are compliant or not? So there's lots of strands that come together when you're trying to solve this very complicated IoT everything problem. So where am I in terms of my initial aspirations? Well, have I addressed accessibility? No. Have I addressed fault tolerance? No. Have I addressed security and privacy? Yes, to an extent I have done that. Understandability is kind of not there quite yet, but data correctness, yes, I'm working heavily on this. So I've got a big gap here at the top, the accessibility and the reliability of my system in terms of fault tolerance, that I think might just be the right thing for Elixir and Erlang in general to address. And I'm probably preaching to the converted here, but there's lots of benefits to borrow from the existing ecosystem. High availability to start with, high concurrency. You don't even need to have one single forever while loop that does the thing you want on your embedded device. You can break it down in tasks, and that alone improves reliability. Significantly improve fault tolerance. You also get to use dedicated communication protocols, or communication between devices can become much easier. It's a given by the thing you're using. We don't need to reinvent the wheel in the world of IoT. And there's been a lot of research in developing tools and applications to have quicker development time. You've got less source code to write. I mean, don't get me started on C again. And then, of course, you've got compatibility for heterogeneous hardware with Elixir, which is a definite challenge in the world of IoT. Once you start having many different IoT devices contacting edge devices of different natures, heterogeneity is going to be a problem. So we've been looking at my lab on the ecosystem that's available to us, and we started familiarizing with nerves. We've looked at Cry10 as another operating system, which I think might just be a very, very good solution for critical IoT systems, like the types that monitor your health or talk to your hospital directly. We've also started looking at NX, and thank you guys for doing that. I mean, I'm not trying to sell anybody anything, but I really have enjoyed looking into that library, and our own eVision library that Coco might have talked about earlier today. I've only recently found out about Explorer and Livebook, and I think I might want to play around with them. But all these tools come together to start providing a basis for over which you can work on IoT, vastly distributed IoT systems, written in a more friendly language than your standard kind of C. I'd be very keen to learn about other projects that are using or targeting learning and federated learning specifically, and other projects that look at tools and stuff for IoT devices. And please reach out to me with information. I'd be very glad to read more on them. So looking at that ecosystem, we put our heads together and we've come up with, well, kudos to Coco for this, with a new approach to doing federated learning, which is implemented in Elixir. We hope to make this open source, and Coco is working at putting together the Git repo. We've submitted our paper just this month to the Elixir workshop hosted at SIGPlan, and if it's accepted, would be very glad to present the whole of the paper to the world. Basically, we've started looking at ways of aggregating individual models at a more granular level based on things that might affect what our problem is. For example, if you use our framework for your smart breaking and entering doorbell alert IoT device, it might just become better at identifying you when it's rainy or foggy and kind of stop spooking your wife, spouse, children, whoever is in the house, your pets, every time you approach the door and it's not perfect ideal conditions outside. So that's the kind of problem we're trying to solve, where a global model might not perform quite just as well as a model trained for particular conditions, for a particular set of environmental or outside factors that affect the problem you're trying to solve. And again, we'd be very happy to chat about that, both me and Coco, if you find us on WOVA or on email or anything. So once we've kind of gone through all this definition of challenges and problems that need to be solved, I think I want to kind of conclude this presentation on a good, positive note. And I think that the IoT domain, and especially this kind of dynamic between what's the edge, what the edge is going to look like, and so on, and the cloud, is going to be the land of opportunities. That's, I think, specifically a great area for further development and for further breakthroughs using Erlang in general, and also the Elixir ecosystem more in particular, because I think that the problems that they are trying to solve in this kind of edge fog computing research domain have already partially been solved when people were putting together, you know, the internet itself, and how packets should be distributed reliably, and how you can do multi-threaded task work allocation or data allocation or pass messages around reliably and so on. So in my mind, this is an area that's going to be quite fruitful. I don't know if the IoT devices themselves will end up being also programmed in something like Elixir or Erlang. I'd certainly would love to see that, but I know a lot of electronics engineers or software engineers that work in the domain that are very used to their own ways using, they've learned to super optimize C code for the tiniest benefit in power consumption. And I can see that there would be some pushback in that area, but I think that this edge is so undefined yet that it gives itself to a lot of opportunities. And I'll end with some questions that I think are worthy of researching further. So yeah, okay, if we're moving machine learning to the IoT devices themselves or the edge, are we saving enough in power because we stopped transferring every little bit of data? And if we're saving enough in power, can we use that power, that battery power, to do sufficient processing that gives us enough accuracy or enough efficiency in terms of computation that we can still run within the same battery budget? So what we've saved from transmitting data, we utilize for a better cause. And then again, I think that the work that's available in the libraries that are available right now in Elixir are looking at neural networks. In particular, tensors are very much used in neural networks. But can we have a library that will provide access to all sorts of other machine learning commonly used algorithms like SVMs and nearest neighbors and whatnot, and trees, decision trees, and so on? And then finally, we haven't really quite yet solved the problem of what happens when we have small local data sets and small visibility, and that startup problem I was talking about earlier. How do we start solving a new machine learning problem when we haven't had enough data to begin with? I don't think this is particular to Elixir. I think this is a generic question for all of the machine learning community to address. All right, I think I've kept within my time, and thank you everyone for listening, and I'll be happy to answer any questions.
Thank you very much, Lito. We've got one question from Nick Visenko in the virtual. Nick there? Nick, are you there? Okay, I'll read. Oh, is that you there? You're not that virtual.
Thank you. Very interesting talk. Learned a lot. Thanks. Just a quick question. You mentioned that those little IoT devices comprise a big network, but rather than kind of working via cloud, they could communicate with each other. Is there like some sort of specified protocol which would allow different IoT devices to communicate with each other? Because they have different hardware, different companies make them. Is it something that exists or even in the works?
No, I don't think it exists. I think everybody currently is using kind of their proprietary whatever protocols they think are appropriate, or whatever open source protocols like MQTT or whatever they think is appropriate for their problem. And I think that is a problem in its own, because we're probably not going to be able to take advantage of opportunities where devices could talk to each other. So it is not done yet, but I think it will be something that in the future might become more of a demand. And so people might end up having to start to think about this problem later on. So for example, if you've had 10 devices in your house, I don't know if any of you have a smart home or something, you know how you have to buy an Alexa, and then you can only buy Alexa compatible stuff because that's the only communication protocol that would work. So I think it will have to come to a point where either we all just use their standard protocol to communicate, or people will start demanding that, well, you know what, I've got this new other device that you don't sell and I still want to use in my smart home, so why don't you open it up to me, or something like that. I think it will end up being a trend.
Okay, thanks for the presentation. It was very insightful. I have a question. Maybe it's not strictly connected to Elixir, but it's in the IoT kind of domain. You mentioned the problem of kind of making decisions at the edge. Like if we want to make a decision in the IoT device, maybe we don't need machine learning all of the time, right? One of your approaches was to use statistical computing. But if we need machine learning, I heard about maybe we could change the hardware that we are running the computations on. So I heard about this company that basically creates like analog programmable chips where you can kind of program the chip and run analog computing instead of digital. Because
so you're talking about FPGAs basically. Yeah. So yes, that's the kind of.
Sorry. Finishing my question, would that be like a solution maybe to the problem, in your opinion?
I think they can. The FPGAs are promising because they can do two things. They can run very complex computation at very low power consumption, and the problem that exists with FPGAs is that it takes ages to reprogram. So, for example, when I was doing my undergrad some time ago, I was programming FPGAs, right? And I would leave the compiler running overnight and then go 3 days later and it was still running, and then go 4 days later to check, and it was eventually compiled. So it depends on how big or small the program you want to print on the FPGA is. So how long it's going to take depends on the actual size of the thing. But I think we will see accelerators like that being available. There is also already some system on a chip kind of boards, like the pink with a Q board that you can program in Python, and it does program the accelerator in an FPGA, and it does consume much less power. So yes, this is a direction, of course. I'm not sure to what accuracy, though, these accelerators perform. I haven't seen a network of them working together and tested, a neural network or something. So I don't know what performance in terms of machine learning they produce.
Okay, thank you. We'll have to wrap it up there because we're kind of running over time. But thank you, Lita. One more round of applause, please.